In this lesson, we're going to learn about mathematical models. Take a look at this graph. Yes, we're talking about zombies and zombieism, something that is contagious. If we take a look at the axes, we have time, our independent variable, the number of people as our dependent variable. The people who are zombies start at a low number, gradually increase, and then exponentially increase, and then level off. And notice the people who are not zombies start at a very high level. Then, when they start to succumb to being zombies, that happens quite quickly. And then that tapers off. This is a good graphical model built on a complex mathematical model about this imaginary syndrome of being a zombie. Or is it? So some other mathematical models are as follows. In this one, we have a fish tank, and if that fish tank is filled up with warm water and it's allowed to just kind of cool off, you can see that we have time on the horizontal axis. It's the independent variable. Temperature here. And in this particular thing, we see that as time goes on, water that started at 82 degrees Fahrenheit gets cooler and cooler and cooler as time goes on. If I wrote a mathematical model of this graph and of this situation, I would say that the temperature in degrees Fahrenheit is equal to -2 degrees per hour times time plus 82 degrees Fahrenheit. I don't know if you can do that yet, but you will by the end of this class period. Let's try another mathematical model. In this one, someone is saving money. I see that we have time in weeks compared to the amount of money. This person must have started out with these $30. And as time increases, so does their savings at a very constant rate. If I wrote this as a mathematical model, I would say the amount of money that a person has is equal to $5 per week times the time, that is what week it is, plus $30. That's the mathematical model that describes somebody who started out with $30, who saves $5 a week, and if I wanted to know at any particular time, I could plug in the number of weeks and solve for the amount of money. Maybe now you're starting to see that these last two mathematical models I made look a lot like y equals mx plus b format, or the equation of line. Here's one more before we get to our binder page. In this case, somebody's fish tank is leaking. The fish tank is leaking less than a gallon a minute, but that's still a lot, 0.75 gallons per minute. That's really going to add up. So our independent variable is time. Our dependent variable is how much water is leaking in gallons. I see that we started out with no gallons, and as time goes on, more and more gallons have leaked. So to write this as a mathematical model, I have the amount of water in gallons is equal to 0.75 gallons per minute times the time in minutes, which I could pick any time. I could plug it in here, multiply it by 0.75 gallons, and I would be able to predict how much water had leaked out of the tank. That is also using this format. Mathematical models are very powerful. They let investors make a prediction on which way the stock price is going to go and how they might invest. Mathematical models are used in forecasting weather, hurricanes. Mathematical models are used in predicting things that will happen with diseases and epidemiology, including COVID-19 spread. So the next thing we will do is use your binder.
Class at home, this is page 69 in your binder. We've seen these types of graphs before, where we have position as our dependent variable on the y-axis, and we have time as our independent variable on the x-axis. So I just relabel that. Instead of saying distance, I said position. We're going to work with this position time graph and put it into a way that your algebra teacher would totally appreciate. So first step, calculate the slope of this line, indicate the points you're using, and show the work. This has already been done for you. So the slope we know, we choose 2 points, and we say the difference for y2 minus y1, so 60 minus 30, and then over here, x2 minus x1, so 20 minus 10, would give us 30 over 10, do the division, or 3 meters per second. Stop the video at any time if you need to look more closely at your paper or write things down. You probably talked about the y-intercept in your algebra class. Can you find it on this graph? Here it is. Wherever the line crosses this axis at time 0 seconds, you could also think of it as where is your tumble buggy, your Sphero, your toy car at time 0 seconds. That particular position or place is called the y-intercept. For us, right here at 0 meters. Write the y-intercept form equation. That means the y equals mx plus b, like you have from your algebra class. But now let's plug in some other ideas. For example, instead of calling this y, let's call it the position. So the position of a toy car is equal to the m, which in this case is the slope. The slope is also known as the speed or the velocity of this car. So for this particular car, the position will be equal to 3 meters per second times x. Well, what's x in this case? In this case, it's the time. So this will be multiplied by the time plus b. B being that thing called the y-intercept. And in this case, it's 0 meters. It's going to kind of disappear on us since it's a 0. So let me say this out loud in words. The position of this car at any particular time could be found if we multiply 3 meters per second times any given time. So, for example, if I decide to figure out where is this car at time 15 seconds, I would say, the position that I don't know, I can find by multiplying the speed of the car, 3 meters per second, also the same as the slope, times 15 plus 0. 3 times 15 plus 0 is 45 meters. Let's double check that. In fact, at time 15 seconds, is our car at about 45 meters? Yes, it is. So this is a handy equation that we've developed for ourselves from the graph, from the line on the graph, where we've used the physics words position and time instead of x and y. And for the slope, instead of m, we have a real number, a real slope. That slope we did get from this line, and it's also the same thing as the speed or the velocity or the velocity. So let's continue on with these problems right here. Create a mathematical model for the graph at the right. Express the slope as a decimal if needed. We don't need to. It's at 3 meters per second already. What are the units of the y-intercept? Well, that would be in meters, although it's 0 meters for this particular example. And so let's fill this in here even neater than before. The thing on the y-axis is the position. The slope that we found is the same as the velocity. In this case, it's 3 meters per second. And what's the thing on the horizontal axis? It's the time. And what was the y-intercept for us in this particular case? It's easy. it's 0 meters. So that's the mathematical model, or some people say the equation of the line, for this particular moving car that we've graphed. A mathematical model gives us an idea so that we can plug in any time that we want, and we could solve for the position. Or if we wanted to, we could plug in any position and we could solve for the time. So just like algebra class, the position of the car could be found by knowing its speed, 3 meters per second, and if you plug in the time and add the y-intercept. Let's try a couple.
Okay, let's try another one. This is from page 73 in your binder. We're going to make another mathematical model based on a graph given to us of something that's real. So let's take a look at the graph. No title, that's not good. But we do see that the independent variable is the time in the number of days. It goes from 0 up to 120. And the mass of something, like how much stuff something has, goes from 0 up to 40 kilograms. If you don't know how much a kilogram is, that's okay. I am about 68 kilograms. So human beings come from little babies being 1 or 2 kilograms at birth up to, I don't know, 100 kilograms, 150 kilograms. So a kilogram is more than a pound. Okay, so let's take a look at the graph. We see where this line is right here. Just highlighting it so we're looking at the same thing. So I think we could agree a general trend is as the days go on, whatever this thing is gets more and more massive as time goes on. It goes up and up and up the mass scale as the time scale goes up. So now I'm going to find the slope. I'm going to pick things that are easy for me to find the slope. So I pick 2 points. So I know that this is at 20. Let's choose this one. And how about this one right here at 80? Looks good. And I'm going to write the coordinates. At time 20 seconds, this object's approximately at 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So at 20, 16. And this one up here is at 80 days, 2, 4, 6, 2, 4, 6, 8, 10. So that's at 30. So 80, 30. So my final coordinates are 80 and 30, and my initial were 20 days and 16 kilograms. And so now to find the slope, I find the rise over run, or the change in the y-axis compared to the change in the x-axis. So here's my y-axis, final minus initial, or y2 minus y1, over the times, or what was on the x-axis, or the independent variable, and the final minus the initial. So I have a 14 over 60, which is the same as 7 over 30. Take out your calculator. .233. Repeating. So every day that goes by, this thing grows 0.233 kilograms, so a fraction of a kilogram, but that could be about a pound. Find the y-intercept. So let me kind of highlight that for you here. The y-intercept is right here. So at 0 days, what was it in kilograms? 2, 4, 6, 8, 10, 12. It looks like 11 to me. 11 kilograms. And then how to write this equation. If I'm going to write it like I would for Mr. Epperly or my math teacher, I would say that y equals mx plus b, and then I would fill in for my m of 0.233, and that gets multiplied by our variable x plus the y-intercept is what's known as b, and that is 11 kilograms. I guess your math teacher wouldn't put the units on there, okay? So this is the way Mr. Epperly or a math teacher would write it. To write it for science class, I am going to change the symbols x and y to what's given to me on the graph. So the thing on the y-axis is the mass. The slope I've already calculated to be 0.233 kilograms per every day that goes by. If I put 1 day, that would not be wrong. Instead of the letter x, I look here on this axis. It should be time. And then the intercept I have found already here at b to be 11 kilograms. So that gives me an equation. If I want to plug in a time or plug in a mass, if I plug in one of those, I'll be able to solve for the other one. What does the slope of the line mean for this graph? You do this one. What does the y-intercept of the line mean for this graph? You do this one. Tell me a story of what's going on in this graph as the days go by. You need to do this part yourself. And now we're at the part to preview your homework. This is on binder page 74. We are practicing what I was just describing above, writing a mathematical model for each graph. Remember, in math class, the equation of the line is y equals mx plus b. For our class, we change two of these parts. We change the y to be whatever is on the vertical axis of the graph, also known as the dependent variable. So I would not ever have the letter y there. I would have the word speed. And then I'm going to change colors here. The m will not really be the letter m. That will be the slope of the line that you find. And finally, this thing called x won't really be x. It will be replaced by the word time, whatever's on the horizontal axis. And perhaps you will have a b, and we wouldn't leave it as letter b. We would look at our graph and we would see what is the value where the line crosses the 0. On the x-axis, it's 0 seconds, but where is it on the y-axis? For in this case, speed. So here's one, and here's one. So the b is called the y-intercept. It's really, where does the line cross the vertical axis at time 0, or whatever is the variable there. So think of this page 74 as having two sides or two parts. Put a divider line down this way. The graph on the left has to do with these two questions. The graph on the right has to do with these two questions. For both of them, write an equation or a mathematical model for the line, and then go ahead and solve for something when they tell you to substitute in for one of the variables.